Welcome back, guys. In the last video, we looked at 13.4, Law of Sines. We're following that up today with 13.5, Law of Cosines. And so Law of Cosines is another tool we have to solve for missing sides, missing angles in a triangle. Similar to Law of Sines, you'll notice that it's written three different ways here in this box. And I would not focus on all of them. I would probably not write all of them down. I would write, once again, the bottom one down. C squared equals A squared plus B squared minus 2AB cosine C. Yes, it's a little long, but it's not too bad. And we're going to go through some examples to show you exactly how it works. So before we do that, what I want to show you is, well, I want to talk about this equation for just a second, law of cosines. It says that C squared, one side length squared, equals A squared plus B squared, so the other two side lengths squared added together, minus 2AB, minus 2 times those two other side lengths, times cosine of angle C. First thing I want you to notice, what does this look like to you? C squared equals A squared plus B squared. If you said Pythagorean theorem, you're absolutely correct. This is actually where the Pythagorean theorem comes from. The Pythagorean theorem is a specialized case of the law of cosines, specialized for 90-degree angled triangles, right triangles. So this is how you can kind of remember this formula. C squared equals A squared plus B squared, Pythagorean theorem, minus 2AB cosine C. So here's what I think to myself. These two side lengths, A squared plus B squared, are going to be the two sides I multiply by 2. A squared plus B squared minus 2AB. And whatever side I put out here all by itself on the left, that's the angle, C squared, cosine of C. That's the angle I'm taking the cosine of. So I think of this formula sort of as outsides match and insides match. C squared equals A squared plus B squared minus 2AB cosine C. So when can we use this? As you notice in this equation, there are 3 side lengths in play and 1 angle. We can use this anytime we have 3 of those 4 parts. Of the 3 side lengths and 1 angle, if we have 3 of those 4 parts, we can use this equation to solve for the missing part. So let's take a look. Solve triangle FGH if F equals 82 degrees, G equals 6, and H equals 4, reading ahead. So if I'm thinking, how do I want to structure this law of cosines? What I'm going to do is say, what angle do I have here? I have angle F, then I'm going to need to put side length F by itself. F squared equals G squared plus H squared minus 2GH cosine of angle F. And that's how I know to put F squared by itself on the left, because I'm using angle F. That's what I'm given. So, okay, I don't know what F squared is, so I'll start plugging stuff in. F squared equals 6 squared plus 4 squared minus 2, 6, 4 cosine of 82 degrees. Could we, on this particular problem, it's going to change here in a second, could we start working this out by hand? Minus 2 times 6 is 12, times 4 is 48, cosine of 82 degrees. Yes, we could start working this out by hand and saying, okay, so this is 52 minus 48 cosine 82s. I know I can't combine the 52 and the 48 because the 48 is being multiplied by something, cosine 82. I could start working it out by hand, but honestly, if I do 52 minus 48 cosine of 82 degrees, I get that answer for F squared, 45-ish. If I plugged in, I'm trying to put my calculator somewhere. If I plugged in the line right above my calculator, just from the start, 6 squared plus 4 squared, try that again. 6 squared plus 4 squared minus 2 times 6 times 4 times cosine of 82 degrees. I still get that same 45. So here's my time-saving trick for you. If, like I said, it's going to change in a second, but if when you write out your law of cosines, you have everything on that right-hand side, you have numbers, values that you can plug in, might as well just plug it into the calculator at that point. We just plug it in as is, we get 45.3197, not D, backspace out of that. So 3197 equals F squared. So if that equals F squared, let's just take the square root. I'm going to use the answer button on my calculator so that I don't round at all. 6.7320 if we round. 6.7320. This is how we can use law of cosines to find a missing side length. The question says to solve, so I'm not done. I got to find the missing two angles. What I want you to notice here is, why did we need law of cosines? Why could we not use law of sines? Law of sines is I mean, it's sine A over A equals sine B over B. It's familiar. We didn't have a perfect pair. We had angle F, but not side length F. We had side length G, side length H, but not their angles. This is where law of cosines becomes really handy. So we used this equation. We plugged values in. We solved. We got F equals 6.7320. Well, now I do have a perfect pair. And so now I'm set to use law of sines, maybe to find angle G. Angle G from side length G. So I'm going to come over here and say sine of 82 degrees over 6.7320, now that I know what F is, equals sine of sine of G over 6. G's and 6's look similar. But I'm looking for angle G. So I'm just going to cross multiply. We've done this in the last lesson. We did this a ton. So 6 times sine 82 degrees equals 6.7320 times sine of G. Divide by the 6.7320. Divided by 6.7320. And then how am I going to get that G out? I'm going to inverse sine both sides. So I'll write it all out. So 6 sine of 82 degrees over 6.7320 equals sine of angle G. So to get G out of that sine, I'm going to inverse sine, and inverse sine of 6 sine of 82 degrees divided by 6.7320 equals about 62 degrees. Now, I want to just make sure that makes sense. So, okay. So side length G was 6, so it was smaller than side length F. So it makes sense that my G would be smaller, my angle G would be smaller than angle F. 62 is smaller than 82. I'm feeling good about life. I did one law of cosines to find side length F. I did one law of sines to find angle G. And at this point, to find angle H, I'm just going to subtract my two known angles, because I know they have to add up to 180, and I think that's the quickest way to do it. So right there, a law of cosines problem. You will only ever have to use law of cosines once when you're solving a triangle, because after that, you should have a perfect pair. You can use law of sines. You can use the 180 trick. All right. Okay, we're going to do one more here. And this one is a little bit different. We still have 3 of the 4 pieces for our law of cosines, but notice that they all equal, notice that the three pieces we have are all side lengths. We don't have an angle. So here's my tip for you in this instance. And the reason why, we'll come back to it in 13.7. So don't worry about the reason why, but if you have three side lengths, start with the largest side length by itself. Use that for law of cosines. So I'm going to come over here and say 11 squared equals 2 squared plus 10 squared minus 2 times 10 times cosine of angle G, because that's what I got by itself on the left. Now, unlike the previous problem, this is one where we do have to do a little bit of work on our own because we don't have everything on the right. We don't know what G is, so we can't just plug it into a calculator. So I would come over here and say 121 equals 4 plus 100 minus 40, it looks like, 2 times 2 times 10, cosine of angle G. So 121 equals 104 minus 40, cosine of angle G. And this is where the most mistakes happen with law of cosines. I alluded to it in the last problem. Can I combine these, 104 minus 40? The answer is no, because it's not really 40. It's 40 times something. And so we can't just steal the 40 off of that product. We can't combine those two, but what can we do? We could move the 104 over. So 17 equals negative 40 cosine of angle G. And in our quest to get angle G by itself, we could divide by negative 40. So 17 over negative 40 equals cosine G. And then how do we get rid of a cosine? How do we get the G out of there? Inverse cosine, both sides. And so we get inverse cosine of 17 over negative 40 is going to equal my angle G. And what is angle G? I'll plug it in. Inverse cosine of 17 over negative 40, 115 degrees. So this is a very obtuse, I shouldn't say very, but it's definitely an obtuse angle. 115 degrees, and that kind of makes sense because it's the largest side. And so we used the largest side by itself on the left. We got the biggest angle, turned out it was obtuse. That's my one law of cosines for this problem. What I would have you do now is pause the video, use your perfect pair of G to use law of sines to find one of the other side lengths. And then once you've done that, use the 180 trick to find the one remaining angle. I might have said side length just a second ago. We're looking for the two remaining angles. Use law of sines to find one missing angle. Use the 180 trick to find the other missing angle. I'm going to work it out on mine, then unpause my screen. So in this problem, we had our 115 degrees for G. I used law of sines in red to find that H came out to be 55 degrees. And that left 10 degrees left over for angle F, which is a pretty small angle. Now, looking at this and thinking about it, it makes sense that F is a very small angle. Look at the side lengths. F is 2 and the other two are 10 and 11. So it makes sense that F is tiny. But some of you might be questioning, well, wait, side length G is 11, side length H is 10. Why are their angles so different? And to answer that question, I'm going to go back to the unit circle. It all goes back to the unit circle. 115 degrees is right about here. 55 degrees is right about here. If you look at their sine values, if you look at their y coordinates, they're really not that different. They are different. There's, the 115 is definitely higher, but they're not that different. So the 11 and 10 mismatch kind of makes sense with their sine value mismatch, their y coordinates on that unit circle. This is also the reason, I'm not going to fully explain, but why I encourage you to use the longest side if you're using law of cosines and you are looking for an angle. use the longest side by itself on the left, and that will ensure that we don't run into that ambiguity from 13.4 of two possible triangles and us getting the wrong one. Using the longest side will prevent that. So not a full explanation, but I'm hoping that makes a little more sense as to why the angle measurements seem so different, even though these side lengths are comparable. All right, so as you've seen in these two examples, we need to be able to use law of sines, law of cosines, always at the same time. But I would always try law of sines first because it's a little more straightforward. It's cross multiplying, and in my experience, there are far fewer mistakes made with law of sines. So on these two problems, I want you to look at them for 10 seconds while I'm talking and see, can I use law of sines? If I can get away with just law of sines, let's do it. But if I have to, I don't have a perfect pair, I'll use law of cosines. So looking at this, the triangle on the left, I don't see a way to avoid law of cosines. There's no perfect pair. You might be saying to yourself, wait a second, what about on the right? There's no perfect pair either. However, we can find that missing angle A because they have to add up to 180, right? It's that 180 trick all over again. So once we find A, we will have a perfect pair. We can use law of sines. What I will challenge you to do now is, if you are feeling confident, if you want to challenge yourself and make sure you really do understand this, pause your video now and try solving these two triangles. If you're not as confident, I'm going to work through it right now. But if you are confident, solve it on your own, then fast forward, skip ahead, and see if your answers match mine. This is a great way to check your understanding. So I'll start with the triangle on the left. We said we don't have a perfect pair, so law of cosines it is. I have angle C, so I know I need to put C squared over here. So C squared equals 11 squared plus 17 squared minus 2, 11, 17 cosine of 42 degrees. This is one of those nice cases. I have everything on that right-hand side. I'm just going to plug it in. So 11 squared plus 17 squared minus 2 times 11 times 17 times cosine of 42 degrees. So 132.0639, is it 39? 38. 132.0638 is approximately C squared. I'll take the square root of that. Again, using the answer key so I don't round. 11.4919. And if you're looking at our triangle, that looks very reasonable. It looks about the same length as 11, so looks about right. I think I'm going to use law of sines now then to solve for angle A. I'm going to guess it's a little bit smaller than 42 degrees because 11 is a little bit smaller than 11.49. So I'm going to come down here and say sine of 42 degrees over 11.4919 is equal to sine of A over 11, right? Law of sines. We've done this a bunch now. Cross multiply, we get 11 sine of 42 degrees equals 11.4919 sine of angle A. I'm going to divide both sides by 11.4919. So 11 sine of 42 degrees over 11.4919 equals sine of A. And we know how to get that A out of the sine, inverse sine. Which means that A equals inverse sine of 11 sine 42 over 11.4919 about 40 degrees. And sure enough, I predicted going into that part of the problem that it would be a little bit less than 42 degrees. That's a nice check to be like, yeah, no, I'm doing this right. Lastly, I know that it needs to add up to 180. So I'm just going to subtract minus 42 minus 40. Looks like 98 degrees is what's left over for angle B. All right, so that's a good example of having to use both laws on one problem, as we've seen a couple times now. Let's do this one. Let's figure out our missing angle first. So 180 minus 72 is 108, minus 48 would be 60. So this has to be 60 degrees. Now I have a perfect pair. And in my book, once I have a perfect pair, I'm just gonna ride law of sines all the way to the finish line. So sine of 60 over 13 equals sine of, I'll do 72. Should get something a little bit greater than 13 over side length B. B sine of 60 is equal to 13 sine of 72 degrees. Divide by sine of 60. B equals side length B. I'm hoping for something larger than 13. 13 sine of 72 divided by sine of 60 equals 14.2764. So 14.2764, which matches my prediction. It is greater than 13. I should now be able to find the smallest side because it's across from the smallest angle. I'll say sine of 60 degrees over 13 equals sine of 48 degrees over side length C. And by this point, I probably don't need to narrate the steps. Cross multiply. Divide. C equals, it should be my smallest side length, 13 sine 48 degrees divided by sine of 60 degrees, 11.1554. And again, that looks very reasonable in this problem. Yeah, 1554. Cool. And I guess I should list out A equals 60 degrees. We found that at the beginning because of 180. So this is law of cosines, and law of sines and law of cosines are more of the algebraic parts of trigonometry. There's a lot of solving these equations, moving things around, adding here, dividing there. But I'm hoping that this practice has given you confidence in knowing that you can use law of sines if you have a perfect pair. But if you don't, but you have three pieces of the three sides and an angle, if you have three of those pieces, you can use law of cosines to solve for the missing piece and then use law of sines and the 180 trick to keep on going. So that wraps up 13.5. Take a look at your practice problems. Let me know what questions you have, and I will see you in the next video.